Okay. So nowadays, researchers have scaled up this language model to a large number of parameters, and people figure out that these large language models exhibit some very interesting emergent capability. And one interesting emergent capability of this ChatGPT is called in-context learning. So here I give an example of in-context learning. So here, this is I interacting with this language model. I input prompt this apple to fruit, sofa to furniture, and bird to what? Then this language model answer me animal. The reason is that, well, apple belongs to the fruit category, sofa belongs to furniture, so bird, well, this language model will output animal. So you can see that, well, this language model seems to learn some relationship of these things in the demonstration, and then apply the learned relationship to this new word bird. And here there's another example of sentiment analysis. So I input the first sentence and then input the sentiment of the sentence, which is positive. Then the second sentence and sentiment, and then the third sentence. So this language model recognizes that this is a sentiment analysis task, and then output the sentiment of the third sentence, which is negative. Okay, so in both examples, you can see that, well, this language model seems to be able to learn some prediction rule, like in the context, and well, these examples, these things can be regarded as like training data, right? So I just threw into the prompt the training data, and then ChatGPT learns something and output upon query a new word, it outputs the corresponding response. Okay, so what is the difference of supervised learning versus in-context learning? Suppose we have a data set xi, yi that are i following some distribution t, and we have a new xn plus 1, yn plus 1. Xn plus 1 can be observed, and yn plus 1 cannot be observed, let's say. Supervised learning predicts this yn plus 1 by training a model fxw using the training data set, by doing some maybe empirical visualization task, and then like output the prediction yn plus 1 hat. And hopefully this prediction is roughly the same as yn plus 1. And in-context learning, the following is more similar to a meta-learning approach, where in the first stage, well, people pre-train a very large model and using a huge meta data set. And then, well, given this data set, well, we just input these xi, y pairs into the prompt, into the input sequence, and then query this xn plus 1. And we hope that this large language model gives us a prediction y hat n plus 1, which is very close to yn plus 1. In this example, you can think about this apple x1, fruit xy1, bird x3, and animal is y3 hat. So this in-context learning is in some sense similar to meta-learning, but it's a little bit different. Well, there are two stages. One stage is like meta-training a model, but the second stage is different. The second stage, there's no parameter updating in this ChatGPT. So we just input the training samples, and then this language model will output this y hat without any training, without training the parameter, without updating the parameters of this language model. Okay, so to better understand the in-context learning ability of these language models, here we perform some synthetic data set. We perform some experiment on synthetic data set. Suppose we look at a data distribution, which is a Bayesian linear model, where beta is as a prior, which is normal distribution, and xi, yi follow this linear model. The noise level is normal 0 sigma square. So it's a very toy model. And we can, well, we can say this is a data set of size capital N, well, this is like x1, y1 to x capital N, y capital N. We concatenate them into a sequence H. And the sequence H is a data set, but it is also a meta-training data point. So a meta data set of size equal N is a collection of this H superscript versus J, where this Hj is H1j, Y1j to Xnj, Ynj. So you can think about each of these Hj's are independent to each other. Each Hj is a different task. The beta associated to different Hj's are different, but conditional on a task, the beta are the same, and X and Y are generated from this model, this Bayesian linear model. And then we can train a GPT-2 model. GPT-2 is a smaller version of ChatGPT. We train a GPT-2 model using this meta data set. And eventually we evaluate the task performance of GPT-2 on a new independent task of this Bayesian linear model. So here, this is the experimental result, where I plot the test error versus the number of in-context samples. The number of in-context samples is this capital N. And here there are 4 lines. The green line is the Bayes optimal prediction, is the Bayes optimal test error. Because this is the Bayesian linear model, you know that the optimal Bayes optimal prediction rule is given by the ridge regression prediction. Or you do some simple Bayes rule, you will see that, well, the Bayes optimal prediction is ridge regression in this task. So the green line is Bayes optimal, which is like this curve. So no predictors can achieve better performance than this Bayes optimal predictor. And the green line is the training transformer. It overlaps with this green line. And if you look at regression with some different parameters, yellow and red line, you will see that, well, it's suboptimal. Okay, so this figure demonstrates that, well, not only this pre-trained transformer can perform some in-context learning, but it can perform in-context learning in some optimal way. Optimal means, like, in this experiment, it's Bayes optimal. So this experiment is not what we discovered, is like already discovered for like maybe a year. So this is just a motivating, like it's just abstracting away the word tokens kind of scenario and move to like Euclidean space, and there is this train a transformer, and it can achieve this Bayes optimal predictor. Very surprising experiment. Okay, so my goal today is just to explain why can transformers perform in-context learning. This is based on joint work with Yubai, Fan Wang, and San Xu. The paper will come out, hopefully come out this week. And this is based on a bunch of related work that formalize this in-context learning and propose some mechanism for this in-context learning. Okay, so let me start with introducing what is a transformer. So we use a standard architecture of transformer. The transformer maybe like is very well known to computer scientists, but for statisticians, let's be slow and look at what is the detailed architecture of this transformer. So a transformer is a neural network. It's a sequence-to-sequence neural network. So the parameter of this transformer, let's say, is theta. So I use TF with subscript theta to denote that this is a transformer with parameter theta. It's a sequence-to-sequence neural network where the input sequence we denote it as H. It's the continuation of H1 to H capital N, where capital N is the length of the sequence. And each HI is called a token. Each token is a D-dimensional vector, where this D, capital D, is called the embedding dimension of this token. Well, in practice, this input of the transformers are the words, but you can think about these words has embedding in Euclidean geometry in Euclidean space by doing some word to vec kind of transformation. So that means, well, you can think about the input of this transformer are just Euclidean objects. And after passing through the transformer TF theta, the output H prime is another sequence of the same shape, of the same dimension, the same length, and the same embedding dimension. And eventually we want to output some prediction y hat. And typically what people do is that just add a readout layer, where the readout layer is very simple. It's just maybe some linear transformation, some linear layer, so that it transforms this H prime to y hat. So here, this reach function is not very important. What's important is this TF theta. The most important computations happen in this TF theta. So by the way, this is like this transformer architecture. I mean, just follow this paper. Attention is all you need. This is the first paper that introduced this transformer. It's a 2017 paper. And we only focus on the encoder architecture, and the same result can apply to decoder, but you focus on some simple case. So in this page, I just treat this transformer as a black box and introduce what are the input and output of this black box. But in the next page, I will go into detail about this black box and see what are the inner structure. So opening up this black box, a transformer is an iterative composition of feed-forward layers and attention layers. So TF theta, this parameter theta, is a composition of feed-forward layers, is parameter WL, attention layer is parameter AL, and then composite another, well, iteratively composite this FF and ATTN things for L number of times. And here it is WL and AL are the parameters of these feed-forward layers and attention layers respectively. The parameters of this transformer is just the combination of this WL and AL. And then I need to introduce what are these FF feed-forward layer and attention layer. So first, let me introduce the feed-forward layer. This is relatively simple. So a feed-forward layer FF is parameter W is a sequence to sequence mapping, where the input sequence, output sequence, the size, the shape is the same as the input output of the transformer, D by N. And W is the parameter is the combination of W1, W2. So, well, if I just write down what is the function here, the function formulas here is just a two-layer neural network with a residual connection structure. W1 is the bottom layer width and W2 is the top layer width. These are the parameters to be trained. And HI is the I's input token and HI prime is the I's output token. So this is a very simple thing. It's just a two layers neural network with a residual connection structure. And here there is a illustrative figure, but here this figure is not the architecture of this two-layer neural network. Here, this error is just the thing that, well, this mapping is token-wise mapping. So there's no interactions among these tokens. So for HI, HJ, there's no interaction in this layer. So HI map to HI prime, HJ map to HJ prime. So HI prime doesn't depend on all the other HJs. The feed-forward layer is like relatively simple, but what's more important in this transformer architecture is this attention layer. So this is the key ingredient of a transformer. And an attention layer is parameter A. It's also a sequence to sequence mapping. The sequence shape is the same as the input output, the same shape as input output of the transformer. The parameter A is a bunch of QKV matrices. And for simplicity, these are just D by D matrices. Qs are called the priori matrix, Ks are called the key matrix, and V are called the value matrices. So let me first introduce what's the formula here. So the formula looks a little bit complicated. In some sense, it looks like a two-layer neural network with residual connection structure, but here this network seems a little bit more complicated. Okay, so let's see what it is. So here we want to update this ice token HI. And the update, well, here we have QM times HI. So QM times HI, we can say this is a query, and KM times HJ, this is a key. And we look at the inner product of the query and the key. So this becomes a scalar, and we pass through a nonlinearity function sigma. And this is a scalar, and multiply the VM times HJ. So VM times HJ is a value, is a vector. And then summation over all the j's. Okay. After calculating this part, we added it to HI. So this is a standard architecture of an attention layer. Well, it's invented by people in machine translation, I guess. Like in machine translation, people say this is the attention structure, and I think it's like it exists even before this 2017 paper. This attention layer exists before that, and it's a little bit hard to understand like why they call it query, key, and value. But maybe the reason of this name, key, query, value, is because these are some terminologies in information retrieval domain. So because when they invent this attention layer, these people are in this area, so they call these names are inherited here. Okay, so this is a single head attention layer. A single head is that, well, here is like QM, KM, VM for fixed M. And typically people will use multi-head attention layer, where we just look at a bunch of QM, KM, VM, and the sum over M from 1 to capital M. So capital M, well, here this is very important. This formula is very important. Okay, so I can go a little bit slower. So, well, what's the difference between this multi-head attention and single-head attention? Well, it's just a single-head attention. There's no summation over M. Multi-head attention, we add a summation over M. M is called the head. The little m is called a head, and capital M is the number of heads of this attention layer. Okay, so there are many like terminologies. Head, query key value. Well, query key value are not very important, but head is very important notion, and we will use this notion. Well, yeah, this is very important notion. Okay. And here there is a figure of this attention layer, but this is not a plot of this. This is not representing this architecture. So here I draw so much arrows because, well, for attention layer there are interactions among the tokens. So for HI prime, it should not only depend on HI, but also it depends on all the other HJs. Okay, so this is different from here, this figure where like for fully connected, for feed-forward layers, it's just a token-wise mapping. Where in this attention layer, there is each token will interact with other tokens by this mechanism. Okay. So this is a full architecture of attention of a transformer, and it's an iterative composition of attention layers and feed-forward layers, and eventually, well, after the last feed-forward layers, we need to read out this y-hatch. And well, these well-known large language models, for example, the BERT, GPT-2, GPT-3, this POM, these models are all based on this architecture with small variance. The most important difference is the size of these models. There are several important parameters of this architecture. For example, L is the number of layers. and n is the number of heads. D is the embedding dimension. So given these parameters, you can calculate what is the number of parameters of these models. As you will see that BERT, well, is like already very big, but nowadays people say this is very small, like 40 million parameters. And the largest model nowadays, like, I don't know if there's even larger model, but the POM model is like, what I know, the largest one is like 540 billion parameters. So this model, POM model, cannot be even stored on a single computer. So you need a cluster to distribute these parameters and train on these things. BERT maybe is trackable, but the POM is already like not trackable like by standard research labs. You need this Google or like OpenAI kind of big companies to have these clusters to train these models. But I want to say that well, all these models are based on this like simple architecture with iterative composition of attention layers and feed-forward layers. Okay, so the next topic is that I want to show how these transformers can perform in context learning. Suppose we have a task, a data set xi, yi, I from 1 to capital N plus 1, following a generalized linear model. Let's use this generalized linear model for illustration. So there, yi is a function of inner product xi and w star. W star is the ground truth parameter. It may be different across different tasks. And well, the input format of this dataset to the transformer, we use this format. So we concatenate xi, yi into each token of this transformer. And then the last token, the n plus 1 token, is a little bit different because we don't, let's say we don't observe yn plus 1, we want to predict yn plus 1. So for the input format, here we take a to be 0. This is a reserved slot for the output of the transformer. And because the dimension of xi, yi may not be the same as the embedding dimension, and downside, the third line here, we insert some zeros, and the dimension of these zeros will fill up the dimension. We're making xy0 the same dimension as the embedding dimension. And these 0 slots, we call them the scratch pad. These are very important. Well, these are very important places where we will show that the most important computations will happen in this scratch pad. And we hope to say that while there exists a transformer TF data, there exists a transformer TF data means that there exists some parameters data. Okay, so that it can perform the following task. It can do some computation on these inputs and fill in the place 0 to be y hat n plus 1. And eventually we will read out this location so that the output will be this y hat n plus 1. And while we hope that while this y hat n plus 1 is very close to y n plus 1. So we hope that this transformer TF data can learn something from this training data set. And so that well, the test error, the loss function applied on this y hat and y is small. And this is our empirical observation. I have demonstrated this observation in this like Bayesian linear model. And so empirically we can observe this phenomenon. So that means the pre-trained transformer using this meta-training approach, like inserting a bunch of these data sets and train these transformers can, upon query a new task, we can it can perform this. It can like get this y hat such that the test error rate is small. Okay, and why this transformer can perform this in context learning? And well, one popular explanation is that transformer can approximately implement gradient descent on the empirical risk. By the way, this explanation well float around in the last year, and there are several papers try to make this gradient descent explanation formally, they have rough ideas of this kind, and at first to make this idea complete. Okay, so what's mean by transformer can approximately implement gradient descent on this empirical risk? So first, this is a empirical risk where suppose we choose a loss function L, maybe this loss function. We hope to make something small, we just choose this loss function. And form an empirical risk associated to the data set xi, yi, and with parameter w. And if we use supervised learning, well, people just look at gradient descent or stochastic gradient descent on this loss function. Let's say gradient descent. So that means we update this wt plus 1 is wt minus that says eta times the gradient of this empirical risk, which is the partial derivative of the loss function times xi. Okay. And we will show that there exists a transformer that can implement this gradient descent step. Okay, so this is the most important slide of this talk. Once that gradient descent can be implemented by a single attention layer. Okay, so here on top, I write down the formula for the attention layer. So ht plus 1 is ht plus the average of this summation over this heads and sigma. Okay, sigma eventually we choose the sigma to be a ReLU function. And act on the inner product of QH, KH eventually multiplied by VH. So this is the attention layer. And here below, I write down the formula of gradient descent on this empirical risk for this particular generalized linear model. And as you can see that while these two formula are similar in many sense, they are both this residual structure here and here. And they are both this inner product. Here, this is the inner product on Q and K, and here, this is the inner product of X and W. Okay, so there are many similarities of these two formula. And actually, we show that there exists a QM, KM, VM for M from 1 to M, such that these two formulas are approximately the same. Okay, so the construction is the following. So let's first focus on here. So HI is a single token is in many dimension D. Remember that we take HI to be XI, YI, and 0 in the input. And this 0 is the place of the scratch pad. We will use the place of the scratch pad to record the gradient descent iterate. So that this XI, YI, WT is like the token, what the token is recording. And we can construct these QM, KM, and VM matrices so that QM times this HI token become WT and 1 with some parameter multiplication. And KM times XYW to be XY. This is just restricting to the first top coordinates. And VM times XYW to be 0, 0 XI times some AM. Okay, so there exists QM, KM, and VM to fulfill this task. This is like simple. So after doing this construction, we will see that this attention layer become the middle formula. And as you can see that here, the middle formula is very interesting. So it's XYW equal XYW plus something that is like a constant times 0, 0, X. So 0 means that, well, we don't update these XY positions. We only update the W position. So we only update the things on scratch pad. And if you look at the formula on what's happening on the scratch pad, you will see that this is WT plus 1 equal to WT minus something like a 2-layer neural network times XI. So you will see that, well, that is very similar to this equation, except that there's a 2-layer neural network and there is a partial derivative of this loss function. So what's remaining to be done is just to approximate this partial derivative of the loss function using a two-layer neural network. And this can be done by the universal approximation property of two-layer neural network with nonlinearity function. For example, we use ReLU nonlinearity so that here this approximation can be done quantitatively, and we can control this approximation error. We can control this approximation error, and we can also control this the propagation of this approximation error across the whole transformer. So this page just demonstrates that, well, a single attention layer can implement a single-step gradient descent. And remember that a transformer is an iterative combination of attention layers and feed-forward layers. Suppose the transformer only has attention layers. Then that means, well, each attention layer can implement one step gradient descent. So, well, if there is an L layer transformer, then it can implement, well, let's say L-1 number of steps of gradient descent, and the last layer attention implement this output, implement this flat height equals F, inner product F and W. So this one is like, this step is simple to implement. It's just the gradient descent is something that is like you need iterative like things to implement. Okay. So you may wonder like what happens for the feed-forward layer? Well, we show that, well, actually these feed-forward layers are very good at implementing proximal function. Okay, so for proximal function is like for example, in Lasso, if you want to solve a Lasso solution, one approach is proximal gradient descent. And the gradient step can be implemented by attention layer. The proximal function can be implemented by these feed-forward layers. So you iteratively have this attention layer and feed-forward layers. You have iteratively the gradient step, proximal step. So eventually this is the proximal gradient descent.
Can you always design a feed-forward layer to approximate any proximal operator?
A fixed proximal operation, for example, the soft threshold.
You can, let's say I'm solving a different problem. You still do it? You know, this the proximal operator that you mentioned is very nice. So there are a lot of other proximal operators.
Yeah, there are different proximal operators, and
some of them don't have closed form solutions.
And
the feed-forward layer still approximate them?
You can, well, some of the proximal function, at least you can use feed-forward layers. You can, for example, the soft thresholding, the what else? Yeah, some simple, yeah.
Projection.
Yeah, projection, yeah. Yeah. Okay. So here, this is our theoretical results. We just show that there exists a transformer. There exists a transformer which is an explicit construction that can output W hat L that is supposed to gradient descent iterate WGDL. WGDL is like the gradient descent on this empirical risk. Okay, for this particular generalized linear model, but can be generalized to other cases. For example, two-layer network, we can show that we can also implement gradient descent on two-layer network. And here there are some important parameters of this transformer. In valuing dimension capital D, number of layers L, number of attention height N, feed-forward layer with E prime, and then the norm of parameters theta. So the norm of theta. Here, this norm, we choose a particular norm, but the norm is not the specific form of the norm is not very important, because eventually when we talk about generalization of the pre-training process, the generalization error will depend on this norm in the logarithmic sense. Okay, so these are important parameters, and this construction, well, is not some construction that is like, well, this construction has this kind of bound on these parameters. So that, I mean, this is a efficient construction, and these bounds are useful later when we talk about how to find such a transformer. Okay. So here, this is the existence result. Here, these are two remarks. One remark is that, well, if you want to find these transformers, well, we can just use, well, okay, this result says that, well, transformers with competitive or better performance can be efficiently found by performing pre-training using particular log functions. This I will talk about this soon, later. And then some empirical evidence shows that these pre-trained transformers are indeed performing some theoretically constructed algorithms, and I will show something about this later. Okay. So because of that, transformer can implementing gradient descent in context. We instantiate this gradient descent on a bunch of different statistical estimation tasks. For example, ridge regression, position regression, or lasso. Okay, so we say that there exists 3 different transformers. Okay, 3 different transformers inside the same architecture. While the layer, well, these are just a transformer like I have shown, but the parameters may be different. Okay, so there's one transformer with some parameter that can implement ridge regression, transformer can implement logistics, and a lasso. That can output y hat that implementing this different algorithm with optimal statistical rate. That means while the output y hat approximates this y with some error that achieve this statistical error. So for linear regression and logistic regression, the statistical error is D over N. G is the dimensional feature X, N is the number of in-context examples. And for a sparse linear model, if we implement that, so if the beta is the prior is sparse, has gradient number of gradient S, the optimal rate is S log D over N. And we show that, well, because transformer can implement proximal gradient descent, and then it can also achieve this. You can also implement this lasso with like this implementing it efficiently and with optimal rate. Okay, so then there's a question of like whether these transformers can be found using some approach, using some training approach. And here we don't talk about optimization. So okay, here we talk about pre-training, but we don't talk about optimization dynamics of the training, but we just talk about whether there's a loss function that can achieve this thing and have good generalization error. And well, here this is the setting of pre-training. Suppose we have meta-data as ZJs for J from 1 to little n that are ID following some distribution, and ZJs are XI-Y pairs that are ID. And we can form some empirical lists that are like the average of these ICL loss on these ZJs, and the theta is the parameters to be found. And we assume that this theta is in the transformer class, where this number of layers has these and the norm are bounded by this L and D prime and B. We do empirical rationalization of this empirical risk on this function class of transformers. And then there's a very simple generalization error bound. This is nothing, this generalization bound is nothing sophisticated. It's just a standard runner connected analysis. You get the generalization will be polynomial in this L and D prime, and logarithmic in this B. B is a norm of this parameter theta divided by square root n. N is the number of pre-training tasks. The number of sample in the pre-training phase. So the number of meta tasks. Okay. And here, this standardization bound will show that it can be concatenated with the previous in-context statistical rate. For example, if these tasks are IV following sparse linear model, and we know like maybe so is a good way to solve it, then the overall error is capital N number of in-context samples and little n number of meta-training samples, because this is like a meta-learning problem. We have 2 sample sizes. Capital N is the in-context sample. Little n is like the number of tasks, and this scales as square root d force over n and s not your capital.
Where does the d force come from?
D force comes from this L square and d square d prime. So if we just plug in here these parameters to that place, we get d to the force. So it's not optimized. I mean, here this thing is not optimized. We just put something here that is like polynomial in dimension, but maybe this thing can be optimized better. Okay, so here we just want to say that, well, this transformer previously this is an existence result, but actually if we use like empirical estimation upon the pre-train in the pre-training phase, like at least statistically, it only requires a mild number of samples to find this transformer. But then there's a question of optimization. Can we use gradient flow method to find this transformer? That is something that should be investigated in the future. Okay, so here there are some simulation results, and here we train 5 different transformers on 5 different tasks. So noiseless linear regression, noisy linear regression is two different noise level, sparse linear regression, and linear classification. And the x-axis is the test error. So we pre-train these transformers using these different meta tasks and divided the test error. And the first star is the test error of a transformer. As we can see across 4 different tasks, linear regression, noisy linear regression with 2 different noise level, and the linear classification, these transformers all achieve, or these pre-trained transformers all achieve the competitive performance is like least square regression and the regression. In the case of sparse linear model, this trained transformer here doesn't perform as good as the lasso is the best representation parameter, but it's close. So this is definitely better than linear regression, but not achieving the best lasso performance. We currently don't know whether this is an artifact of the pre-training, this like training dynamics, or it's a limitation of the architecture. Okay. So I think this is like already surprising, but I will show you some more surprising experiments. Okay, so here there is a surprising experiment that I will describe. Let's suppose we have 2 meta tasks. One is regression task, the other is classification task. In regression task, we have that beta acquired, which is normal zero identity, and the y is linear function of x. In classification task, beta is normal zero identity, y is a logic function of x and beta. We train 3 transformers, and they have the same architecture, but they may have different pre-training process. So we have trained a TF-reg on these regression tasks. That means like we generate a bunch of these data sets that follow this regression task, and we use like other algorithm, reinforcement algorithm to train this TF-reg. And for the second transformer, TF-CLS, we train it using the classification task. And we train a third transformer called TF-unnamed using the mixture of regression task and classification task. Okay. So unexpectedly, we know that this TF-reg can perform this linear regression, and TF-CLS can perform logistic regression, as we have shown before. The question is, what algorithm does this TF-unnamed perform? Well, in pre-training phase, we have 2 sets of different tasks, X, Y, I's. We train this TF-unnamed. And then in the test phase, we just randomly choose a task, maybe regression task and or classification task, and put it into the transformer and ask, what's the output of this transformer, of the second of this TF-unnamed. Okay, so well, the surprising thing is here. So well, we can call this TF-unnamed. We give a name called TF algorithm selection. The left-hand side, this is the regression task, test error versus number of incomplex samples. Right-hand side, this is the classification task, test error versus number of incomplex samples. The left-hand side, the best algorithm linear least square, like this is like the dashed line. So this is the test error of least square. You can see that, well, both TF regression and TF algorithm selection achieve this least square test error, whereas the TF-CLS trained on this TF-CLS is trained on the translation task. It doesn't give you the good performance on this regression task. This is expected because, well, in meta training phase, you didn't let transformers to see these kind of tasks, so transformers cannot learn this thing. On the right hand side, well, the dashed lines is the performance of logistic regression here. And we see that TF-CLS and TF algorithm selection achieve this dashed line, whereas TF-REG, TF trained on the regression task is suboptimal. Okay, so that means this TF algorithm selection can achieve the best performance on both tasks. And remember that, well, in the test phase, I don't tell this transformer whether you should perform regression task or translation task. If this transformer is only implementing one algorithm, either regression or classification, it cannot get this performance. Okay, so the empirical result I summarize it as this TF algorithm selection selects a proper algorithm on this task to perform. And this is like what statisticians do in data analysis. But you can not only implementing this ridge regression, this logistic regression, but you can also like think about, look at the data set, which algorithm I should choose to implement and then like get the best performance. This is another surprising experiment following roughly the same idea, but these are two different tasks with linear model with small noise, linear model with large noise, Bayesian linear model with this small and large noise. So you know that the best performance is achieved by Bayesian predictor, which is ridge regression with a particular parameter. And as you can see that, well, the TF algorithm selection achieves Bayes' optimal performance on these two different tasks. So although these are both linear model with some noise level, but the noise level are different in these two different tasks. So if you just use a single ridge regression with a particular regularization parameter, you are not able to achieve the best of both worlds. You need to select properly the regularization parameter to be able to achieve the best performance of these two different tasks.
What was the between tasks? So you had two populations of regression with small and large noise.
Right, and train TF noise 1 on the small noise, TF noise 2 on the large noise, TF algorithm selection on both.
The noise from the error curve. The noise from the error curve of the regression.
There are some noise on the regression.
So the sigma square of the regression of the error curve.
Yeah, small noise is like small sigma square, large noise is large sigma square. Yeah. So this experimental result that says that this TF algorithm selection can select regression with optimal regularization. And this is also like what the statisticians do in data analysis. The statisticians not just do a regression with a fixed parameter, but the lab just look at different regression parameters and select one that perform the best. Okay, so I want to theoretically explain how transformers can perform algorithm selection. So then the first question is like, how statisticians perform algorithm selection? Well, there are arguably two strategies. Well, strategy one, run K algorithms. So you don't know what algorithm to run. So you run K algorithms in parallel, select the algorithm with the smallest validation error. Okay, so you first run algorithm and eventually you do sample, okay, you do sample validation, you do like pre-validation splitting, train on the train and validate on the validation stack and look at the one with smallest error. The strategy 2 is like perform a hypothesis test before select the algorithm. If you feel like this data set should be do classification, you should you can test what's the y is like real, you should perform regression. Y is binary, you should perform classification. Right. So this is like hypothesis test to test whether y is real or binary. And we will show that transformers can efficiently implement these two mechanisms. Mechanism one, post in ICL validation. Okay, so after income test learning, it validates using the validation set. Mechanism two, pre-ICL testing. Okay, so here this is the post ICL validation mechanism. I will not go into detail, but if you trust me, just what we show is the following. So there exists a transformer that can perform the following: 1K different algorithms on the training data set. So this is the input format, right? So this is x1 to xnt. I say like this. I choose the number of training data set training point to be nt and perform training on this part using L-stack gradient descent with L-layer transformer. The second step, choose the prediction function that minimizes the loss on the validation set, dy, which is the second part of this data set. And after choosing the prediction function that minimizes the validation error, we just predict y hat using that particular prediction function. And in total, this part uses 3 layers for like validation, for evaluating the validation error and select the algorithm. Okay, so theorem that could be shown in this case is that, well, for this baseline linear model with different noise level, we can show that there exists a transformer that uses post-ICL validation mechanism to efficiently and which regression is optimal representation parameter. Such a transformer can be pre-trained efficiently. That means the parameters like D, L, M, and prime norm of data can all be efficiently bounded so that the generalization error is small. The generalization error in the pre-training phase is small. So this explains this experiment where linear model with different noise level, while there exists, well, if you train on both tasks, then this transformer can perform the best of both worlds. Well, here this is a different mechanism of pre-ICL testing mechanism. So suppose we want to wonder whether do regression or classification. What we do is that we don't need to run K algorithm in parallel. If we run K algorithm in parallel, that requires the scratch pad to be very long. We need to perform a lot of computation, but perform K algorithm in parallel that take up a lot of memory. But if we know that this is like regression versus like correlation test, then like just do a binary test of this y. So if y is 0, 1, we just do the binary test to say we just do classification. So there exists a transformer that performs the following: perform a simple hypothesis test on the data sets. We can there are some different maybe binary tests or some other test function. Maybe for other different tasks, maybe can implement different test function to decide which algorithm to choose. This uses constant depths, constant layers of this transformer. And then, well, after the test, we just select algorithm to run on the whole data set and predict y hat n plus 1. Okay, so for this particular classification versus regression task, theoretically show that there exists a transformer that uses the ICL testing mechanism to efficiently implement linear regression on regression task, implement logistic regression on classification task. Such a transformer can be pre-trained efficiently. So this explains this experiment where in this tree transformer can this figure. Okay, so let me summarize. So today I presented this ICL property, the in-context learning capability of these large language models. These are some emergent capability when people scale up these language models to a large number of parameters. People found that these transformers can do the following things. And what we do is that we theoretically explain why transformer can efficiently implement these basic ICL algorithms using gradient descent mechanism. The basic ICL algorithms include linear regression, logistic regression, Dassault, And actually we can show some other like layers network. And the second part is that we show that the transformer can efficiently implement algorithm selection. This is like what statisticians do in practice. And while these transformers can be pre-trained statistically efficiently, and yeah, the paper will come out this week. Thank you. Any question?
I just wanted to clarify, like the pre-training procedure. I guess I didn't completely understand it. When you're pre-training on these regression tests, are you changing the weight parameter, like, or are you training on the same weight parameter?
Different parameter. So the weight is sampled from the prior normal zero signal, normal zero identity.
And then I guess a follow-up question. So all these existence groups, I guess, implicitly depend on the structure of the data that you're feeding in, but maybe empirically you show that structure and still get good performance.
You mean the structure? The structure means like this, like X, I, Y, 0, this structure. I think here there are some different structures you can use. I mean, you can think about there are some layers of transformers that can transform the structure to be this. So if the input is some words, well, you can first transform the word to Euclidean object, Euclidean vectors using like word to white or some fixed transformation to make it Euclidean object. And well, if there are X and Y not in the same token, you can move the Y to the same token of X. So that's like one a simple layer transformer attention layer can implement that. So if the format is not like this, actually we use this format in our architecture and also use the different format in this GPU2. The different format is that we input x0, 0y, x0, 0y. So using that format into the GPU2, and it has a simple format. It's not too big. Yeah.
Thank you for the presentation. It's very insightful. My question first is about how does this framework, is there a fundamental difference between this framework and the more classic natural learning approach, or is it appropriate to say that this framework is natural learning, but with transformer, which is more powerful model?
Okay, good question. Let me think. So you're asking like, well, this is like a meta-learning approach.
Yes.
And there are like other meta-learning approach like training to like learning to learn kind of thing. And there is one difference of this in-context learning with learning to learn approach, which is that while learning to learn require pre-train, fine-tune, where in these transformers, this ITL is just pre-train and then not fine-tune. Fine-tuning is you need to update the parameter. And here you don't in language model, it doesn't fine-tune, you just input X and Y pairs and then like output this new one. So actually this in-context learning, this concept is proposed in this GPU3 paper. This large language models are future learners. So they propose, well, they describe what this transformer seems to do meta learning, but the difference is that they are doing the meta learning in a context. So I think I don't want to advocate this approach better than like I don't want to say like if you want to do meta learning, whether you want to do using this language model or using the previous meta learning. I don't want to allocate either. I just want to hear this is just the explanation of like why this transformers can perform this in-context learning, but well, whether this can be better than the other meta learning approach, I don't want to say something. Yeah, I must say something.
Just one more follow-up question on that. So, in this work, you presented the framework, which an explanation to explain why a transformer can do in context learning by showing its ability to approximate the gradient effect. So, in this is the discussion about the regression task, like prediction task, but does this carries the potential of expanding to any form of in context learning, like back into the original in context learning via natural language?
Yeah, so my understanding is that should these like XRY kind of predictions like particular in context learning, or there could be other in context learning, for example, like Markov chain and time series data or decision making or yeah, so there are some other things, and the question is like whether this is generalizable. I think it's generalizable. We are trying to generalize this to a bunch of more general scenarios, and actually we are also trying to use this into understand using this approach to understand chain of thought, like some interesting phenomenon where you just use some chain of thought demonstration, you get better performance by some. Yeah, so I think it's generalizable. I think it's interesting. It's a powerful framework where you can generalize this to like other in context learning case. Thank you.
So like you on next this for the algorithm section do the same balance like
Balance data means the same number of data points in different tasks. Yeah, in the experiment we use the same number of data points. The capital N is fixed in the experiment. Yeah, we didn't check. We didn't check whether like if we do different capital N in different tasks, what will happen? I think it will be similar. I don't expect this already.
The second question is that you should like transformer achieving optimal in this algorithm. Like when you were doing experiments, is there any algorithm that like just like fails the transformer first?
Yeah, there are the lasso is like the we try very hard to train this sparse language, and if we don't do some particular tricks, the lasso will be this sparse linear model. In this sparse linear model, this transformer will just linear regression, because like the transformer, we didn't have transformer that this is sparse linear model, so transformer like just didn't recognize that this data is sparse. So we use some tricks to train this transformer to make it the behavior better, but still not the best. So this is the case where like transformer fails. Yeah.
Is it because the approximation for the proximal not good enough? That's where it fails, or because you have such an approximation?
Well, actually, theoretically, if you want to implement this proximal function, it just needs just two values. It's not so hard to implement this proximal function theoretically. Actually, theoretically, we don't even have approximation error for transformer to implement this lasso. Theoretically, yeah. So I think it fails. What maybe one reason is maybe like the optimization. Well, they show that it can be found used efficiently by doing ERM, doing the interval optimization, but here this optimization algorithm may not be good enough. We try to like we try different optimization algorithm, even design some other loss function. We call it guided tree. We use like the ground truth. We add a loss function which measure distance between like the W hat and the ground truth W, and through this way of training perform this item. Yeah. Currently, we don't know what happens. We don't have a very sure conclusion about what happens in this space. I heard that there are some other groups working on this, also observe similar phenomenon where implementing weak is simple, but implementing some base and linear model with like sparse fire, that's that's not so simple. So yeah, I think that's an interesting question to be investigated further.
One more question. I don't know.
Mhm.
Green, do you want to unmute?
Oh, hi. Yeah, hey. Hi, Song. Thanks for the great talk. So it's very interesting. So I just want to hear about your thoughts about, for instance, if let's say the pump that very short, right? So here the in-context learning from real result seems like you need to have an n to be very big to have a small error, right? So but in practice, we use a very small, very short pump that you can still get some satisfying results. This kind of thing might not be for my algorithm using gradient descent, for instance, right? What are your thoughts about those?
Yeah, good question. Yeah, so the question, let me rephrase the question. The question is that the example, let me correct me if I'm wrong. So here in these examples, we only have 2 data points and you can have a good prediction. But
Yes.
yeah, but like the theory, well, these theories require like a lot of like, well, the statistical require the number of samples be the same as dimension. So my thought, well, I have like maybe like 2 explanation. One explanation is that, well, maybe you can think about like transformer is implementing this lasso, right? So if you want to implement lasso, maybe like, although you only have 2 samples, but maybe like there's a linear model and this linear model is like sparse, the y is like a sparse function of x and the beta is sparse enough. So s maybe is like 1 or 2. So if that's the case, then like you don't need a lot of samples to implement this lasso thing. So that this is like one possible reason. Another reason is like maybe like the signal to noise ratio is too high. Yeah, in this real data things. I know like people say like ImageNet, like this kind of thing, like have a very high signal to noise ratio. People human can do like can predict very well, right? So that means signal to noise ratio very high. So I guess like in language, maybe like it's also because the signal to noise ratio very large. So like you don't need maybe like, okay, so Apple can be embedded in 1,000 dimension, but maybe it's lying on 2 ambient dimension. So
I see.
like why? Yeah, but these are just some random thoughts. It's not some like it's not some thing like serious. Yeah. So, but very good question. I think it's a good question to be thought further. Yeah.
All right. Yeah. Thanks.
Thank you.
Maybe this is legal. So yeah, go ahead.
Oh, yeah, I have a question about the generalization error of the transformer
Yeah.
class. How do you deal with the complexity of the
Yeah, very interesting thing is that this is a trivial transition without parameter counting. Yeah, also if you do parameter counting, the transition error will be the number of parameters times log of the norm of the parameter. That means some Lipschitz condition, but the Lipschitz is quite good. So that means this is a trivial transition bound. It didn't use like the sophisticated result in the neural network literature. But I think the result is not too bad. It's like normally the logarithm can be. If you the question is like, can we use some more sophisticated transition bounds that some better? That is something we didn't optimize. Maybe this is much.
Do you happen to know is there any existing literature that analyzing the like attention levels there, like generalization?
Yeah, I know there is at least one work I know analyzes translation of attention. They use some like a little bit sophisticated translation technique, which is falsification ladder. This is by the group of Shanghai or the Shanghai is Civil John, the group of Microsoft. Yeah, they do some generalization analysis like that, but we didn't use that. We just use a very simple parameter counting. The reason, maybe the reason why parameter counting is enough because, well, the approximation doesn't require too much layers, too much text. So the approximation part is like very good, so that we don't need a very sophisticated generalization model.
So you also counting those like a Q way.
Yeah, Q, W, the parameters, Q is D by D, W is D by D. So this word, and this word is like the number of parameters for the attention layer. D prime is the number of parameters in the connected layer, or C4 layer. One L comes from L number of layers. Another L comes from the Lipschitz constant, log of Lipschitz constant, and this log B. Yeah. So it's just parameter counting.
Okay. So the technique you use to analyze this like related to like sparse or linear regression, or like
You're doing this. It's a standard thing. It's like you have architecture with D parameters. Your generalization is square B over N, something like that. Yeah.